Okay, in this part, let's work on the percent composition first, and then let's move to empirical and molecular formula calculations, and I will finish this video with stoichiometry on equations. All right, so let's say, what is percent composition? Percent composition is the percentage of mass of each element in the compound. So mass percentage of every element in the compound is called percent composition. But what is mass percentage? For example, for element A, for component A in a compound, the mass percentage is mass of that component divided by the mass of entire sample times 100, because it's a percentage. So mass of component A divided by mass of sample times 100. So as an example, let's work on CH2O, which is a toxic gas. We are going to find the percent composition of this compound in a 30-gram sample. So first, look at the elements in this compound: carbon, hydrogen, and oxygen. So let's find the mass percentage of carbon first, then hydrogen, and at the end, find it for oxygen. So let's do it for, let me change the font. Percentage of carbon. How many carbon atoms do you see in this molecule? You just need one, right? You just see one. What is the mass of each carbon atom? 12.01. And what is the mass of entire sample? It's given as 30 grams times 100. I have the answer. So it is 40%. Okay? For percentage of hydrogen, how many hydrogens do you see in the formula? 2, right? So make sure you include it. Times 1.01 mass of 1 hydrogen, again divided by the mass of entire sample. The answer for this is 6.73%. For calculating the percentage of oxygen, you have two ways. You can repeat the same calculation fraction for oxygen, 1 times 16 divided by 30, or you can say percentage of oxygen is 100 because the sum of mass percentages of the atoms is equal or very close to 100. So percentage of carbon plus hydrogen plus oxygen must be almost 100. So you can calculate the percentage of oxygen as subtraction of 100 from 40 plus 6.73%. And put a percentage here. So it would be 53.3%. That's how you find the percent composition of a compound for carbon, for hydrogen, and for oxygen. All right? That's easy, just working on one formula. The next concept you have in chapter 3 is talking about empirical formula. Empirical formula is the simplest whole number ratios of the atoms you see in the molecule, so in the compound. So in the molecular formula, I mean in the formula, not in the molecular formula, in the formula of the compound, you see some moles, some number of moles, some numbers. If this is the simplest whole number ratio of the atoms, it's called empirical formula, which you need to calculate first. And then in its molecular formula, you will see the actual number of atoms which exist in the compound. Let me just give you an idea of the examples, like what would be the difference between empirical and molecular formula. For example, for an organic compound which is called benzene, we have CH as the empirical formula of this compound. So what's the ratio? 1:1, right? But its actual molecular formula is C6H6. So So you see the ratio here is 6 to 6, which is actually 1 to 1 when you simplify it, but the actual number of atoms is given while its simplest whole number ratio is just CH. Let us move towards this example to have a better idea of what we have in these types of problems. An analysis of sodium dichromate showed these: 17.5% sodium, 39.7% chromium, and 42.80% for oxygen. We're supposed to find the empirical formula first, and then the molecular formula if we know that the molar mass of this compound is about 262.0 grams per mole. So I told you, we first need to find the simplest whole number ratio, or we need to find the empirical formula first. Write these percentages here. 39.7 for chromium and 42.80% for oxygen. Percentage is difficult to deal with for these calculations because, why? Because in the formulas you never see anything as a percentage in the formula of the compounds. You just see the moles. So we have to find a way to change this percentage to mole. But first, let's assume that we have a 100-gram sample, okay? For all of these elements, okay? So if we consider a 100-gram sample, what does 17.5% mean? Means 17.5 grams out of 100 grams, right? So you just simply change 17.5% to 17.5 grams, right? We assume the sample weighs 100 grams, so 17.5% means 17.5 grams out of 100 grams. The same assumption for the rest. So 39.7% of chromium changes to 39.7 grams of chromium. And for oxygen, it's going to be 42.8 grams of oxygen. Okay? Now, again, our goal is to use moles in the formulas with their empirical or molecular formula. But what you see here, you still see something else. It's mass. How do you change the mass to mole? In the previous video, the very first type of calculations, you remember the relation between mass and mole is done by using molar mass. So you divide all of these atoms by their molar masses. Molar mass of sodium is 22.9 grams per mole. For chromium is 51.99, almost 52 grams per mole. And for oxygen is 16 grams per mole. So the answer for these divisions for sodium is 0.761 moles. For chromium it's 0.763 moles. All right, and for oxygen is 2.68. Moles. We are running out of space here, so let's move towards the next page. So one more time, let me just write them as 0.761 moles of sodium, 0.763 moles of chromium, and 2.68 moles of oxygen. Okay? Now, again, these are moles. Now, finally, we got closer all the way from percentage to mass, and now we have moles. But have you ever seen any decimals in any formulas? No. So you have to get rid of the decimals and change it to the simplest whole number ratio. We must have whole numbers, right? What is the solution is to divide these numbers by the smallest of these numbers. So which one is the smallest here? The first one, right? 0.761. 0.761. Divide all of them by this smallest number. So, how many moles of sodium you will have? 1 mole, right? Almost 1 mole for chromium. But you will have 3.52 moles for oxygen. We are doing good. We're really doing good. 1 mole, 1 mole. The only thing that needs to be modified again is the number of oxygens, which is still not a whole number. You already did your division, so this time you need to multiply by a number that changes this number to the smallest whole number closest to it. What is it? It's 2. So don't forget to apply this on all of them. Now, you will have 2 moles of Na, 2 moles of chromium, and tell me how many moles of oxygen? 7 moles of oxygen. Bravo. This is empirical formula of sodium dichromate. Empirical formula, which is Na2Cr2O7. Okay, you are done with empirical formula. If you remember, we are supposed to find the molecular formula as well, and the molar mass is given, 262. There is a relation between molecular and empirical formula that I would like to write as a formula for you. It seems like molecular formula is empirical formula. We said empirical formula has the smallest whole number ratio, right? So it seems like if you multiply the subscripts of empirical formula by a number which is called n here, you will find the subscripts for molecular formula. So your goal should be finding n. N is mass of, let me just write down MF as molecular formula, and divided by mass of EF, empirical formula. Now, the mass of molecular formula is always given, and mass of empirical formula, you can calculate it easily because now you have your empirical formula, right? So let's do it together. The mass of molecular formula was given, which was 262 grams per mole. Okay, so N is 262 grams per mole divided by mass of 2 times 22.9, which is sodium, plus 2 times 51.99, which is chromium, and let me just make it more clear to read, plus 7 times oxygen. Okay? If you do this calculation, it's going to be the same, 262 almost. So N in this case is 1, means that molecular formula is equal to empirical formula in this case, and both of them are Na2Cr2O7. If N was a number greater than 1, you should have simply multiplied these subscripts by the number. For example, if N was 2, you would have said this is Na4Cr4O14. Okay, so here that was the simplest N1. So empirical and molecular formula are the same, and it is correct for sodium dichromate. Tired? Let's go to the last part of this video, which is called stoichiometry. Stoichiometry of equations. Any calculations we do on chemical equations, we call them stoichiometry. So let's see, we have this equation. Nitrogen reacts with hydrogen to produce ammonia. Let's go from mass of nitrogen. We have 6.86 grams of nitrogen started reacting with hydrogen. We want to find out how many grams of ammonia is produced. So we are given the mass of N2 nitrogen. Then we are going to go all the way from mass of nitrogen, which is 6.86 grams, all the way to mass of ammonia. Okay? Ready? You need to find a relation to switch from nitrogen to ammonia, from N2 to NH3. Let me walk you through it. So we are going from mass of nitrogen to mass of ammonia. First, you need to change the mass of nitrogen to moles of nitrogen. Then this part is the relation between the two substances. You see how we switch from N2 to NH3? And then after you find the moles of NH3, you use the molar mass of NH3 to find its mass. So again, start with the given value, 6.86 grams of nitrogen. Use the molar mass of nitrogen to change the mass to mole. So 1 mole of nitrogen, it's N2, huh? So watch out. 2 times 14, which is 20, right? Grams of N2. So far, you eliminated grams and grams, moles of N2. You are here. Next step is to relate N2 to NH3. That's when you need to look back at the equation. Tell me, according to this equation, how many moles of nitrogen do you have here? You don't see anything, so it means it's 1. So 1 mole of N2 produce how many moles of NH3? Do you see this 2 here? So use this 2. 2 moles of NH3. So now cancel moles of N2. You are here. You have one more step left, which is using the molar mass of NH3, which is, if you calculate it, it's going to be 17.03 grams. Do this calculation in your calculators. 6.86 times 2 times 17.03 divided by 28. Did you find the answer? It is 8.34. Is that correct? And one more thing that I want to tell you, please, when you are using the molar mass, the number here is 1 and here is 1. Don't look at the equation when you're using the molar mass. Molar mass, as we said in the previous video, is a mass of only 1 mole. The only time you are allowed to use these equations is when you want to switch from one substance to another substance. You are jumping from N2 to NH3 here. You see that? But when you are using the molar masses, you are not allowed to use any numbers but 1 because it's the mass of 1 mole. Alright, so this example shows you how to go from one side to another side. But I don't want you to think that you are giving the mass of reactant first and you will be asked for the mass of product. What if you are given the mass of product, you're going to find out the mass of reactant. I gave you an example here to work on. Again, I use the same equation. Let's find out what mass of H2 what mass of H2 is required to produce 8.34 grams of NH3. Okay? So you see, you can go from left to right or right to left for these types of calculations. Now, put the pathway. You are going from mass of NH3 to moles. Then from moles of NH3 to H2. Jump here, that's the conversion here. And then you will use a molar mass of hydrogen. Ready to calculate it together? All right. Start with the given value. What is the mass of NH3? 8.34 grams. Find the molar mass of NH3. You already did in the previous example, which is 17.03 grams. So cancel mass of NH3. Now it's time to relate the moles of NH3 to moles of H2. I told you that's the only time you look at the equation. Tell me, what is the number of moles of NH3? Do you see 2? 2 moles of NH3. And how many moles do you see for hydrogen? Do you see 3? 3 moles of hydrogen. So now you can use, the last step is what? Here, use the molar mass. 1 mole of H2, watch out, it's 2 atoms, so 2 times 1.01. When you calculate it, everything on top divided by everything on the bottom, you will end up having 1.48 grams of H2. So I want you to write down your pathway always whenever you're working with stoichiometry calculations, so it shows you how to move and what type of conversions do you use. And again, one more time, I repeat so many times, I would like it to stick in your mind. When you are using the molar mass, don't use any other numbers but 1, because molar mass is a mass of 1 mole. All right, are you ready for limiting reactant and percent yield? Take a break and open the next video whenever you're ready, okay?